Welcome to class, Focus Learners. For today's explainer, I'll be your professor as we completely shatter the persistent misconception that chemistry is a strictly modern invention. When we hear the word chemistry, we naturally picture sterile white laboratories, complex glass beakers, and modern researchers in safety goggles. But the truth is, the fundamental manipulation of matter actually began millennia ago. Today, we're going to explore the absolutely fascinating historical contributions to chemistry in ancient India, uncovering how early civilization mastered metallurgy, medicine, and even conceptualized early atomic theories long before the modern era. Okay, let's take a quick look at our syllabus for today. We're going to trace the origins of alchemy, explore Indus Valley manufacturing, decode classical texts, touch on ancient cosmetics, examine the very first atomic theory, and finally connect ancient matter to our modern measurements. Let's jump in.
Starting with Section 1, the origins of alchemy. We're looking at the historical and honestly sometimes mythical origins of the discipline. You know, historically, folks weren't just studying chemistry for the sheer fun of it. They were driven by what you might call the ultimate ancient side hustles. I'm talking about the Philosopher's Stone, which was supposed to turn base metals like iron into pure gold, and the Elixir of Life, basically the world's most extreme anti-aging skincare routine. But here's the wild part. While chasing these total myths, ancient Indian scholars accidentally birthed Rasayan Shastra, the actual practical science of chemistry. This pursuit resulted in very real, highly practical breakthroughs in metallurgy, medicine, and the manufacturing of cosmetics, glass, and dyes.
Moving on to Section 2, Indus Valley chemical manufacturing. Let's see how these early concepts were applied on a massive industrial scale.
When we look at the timeline of archaeological finds from early Indian settlements like Mohenjo-Daro and Harappa, dating all the way back to 2500 BCE, we see the mass production of baked bricks and pottery. Now, this wasn't just basic arts and crafts. Mixing specific materials, molding them, and using controlled fire to get highly durable products, that is literally the world's earliest chemical manufacturing process. Fast forward to 1000 BCE in Mosky and Taxila, and they were actively coloring glass using metal oxides. Plus, we see techniques for leather tanning and cotton dyeing documented right in the Rig Veda era.
So the big takeaway here is that these folks weren't just making basic tools. They were actively manipulating the chemical properties of elements. They melted and forged lead, silver, gold, and copper. And get this, they realized pure copper was often too soft for certain jobs, so they actually toughened it up by alloying it with tin and arsenic. That's essentially the ancient equivalent of modern structural engineering. They developed indigenous extraction technologies to pull these metals out of the earth and refine them, which absolutely requires a profound empirical understanding of material properties.
All right, Section 3, Classical Texts and Chemical Recipes. Let's look at how ancient scholars meticulously documented these complex reactions for future generations.
These classical texts were basically the ultimate laboratory manuals of their day. For instance, the Sushruta Samhita details exactly how to prepare complex alkalis. Then you have the Charaka Samhita going even further, outlining methods to synthesize strong acids like sulfuric and nitric acids, along with various metal oxides and sulfates. And the Brihat Samhita? It acts like an encyclopedia, giving us exact recipes for plant-based, glutinous resins used to reinforce the durability of walls and roofs. They were actively standardizing their chemical processes centuries ago.
If you want proof that this stuff worked in the real world, just look at the famous wall paintings of Ajanta and Ellora. These artworks still look incredibly vibrant after ages. So the next time you're admiring ancient art, remember that those lasting colors and structural integrity didn't happen by accident. It's the direct result of highly advanced botanical-based chemical engineering. They boiled down extracts from plants, fruits, seeds, and barks, and then treated them with resins to create these incredibly long-lasting binders and pigments.
On to Section 4, Ancient Dyes, Cosmetics, and Soap. Let's pivot to the chemistry of everyday life and ancient hygiene.
This is brilliant. The ancient scientist Chakrapani developed a method for manufacturing soap that is a perfect historical parallel to the chemical separation and synthesis methods you do in a university lab today. He basically invented early soap using a highly precise mixture of extracted mustard oil and local plant-based alkalis. When you mix fats or oils with an alkali, you trigger a chemical reaction called saponification. Chakrapani was performing deliberate, targeted organic chemistry just to improve human hygiene.
And it went way beyond soap. These ancient techniques expertly isolated pure chemical compounds from botanical resources. They were scaling up the manufacture of agricultural fertilizers and dyes for mass use. We're talking indigo and iron powder for hair dye, and turmeric, madder, and lac for tinting fabrics. They even had entire treatises, like the Gandia Euclid, dedicated entirely to formulating scents, talc, and incense. And we definitely can't ignore their mastery of biological chemistry. They understood exactly how to ferment barks, cereals, and sugarcane to create various liquors known as ossivas.
Section 5. The First Atomic Theory. Class, we've reached a pivotal moment in our syllabus where philosophical speculation beautifully meets hard science.
So who really discovered the atom? Think about that carefully for a second. If you ask a student in the West, they'll likely give you one specific answer. But the reality is, the answer totally depends on which continent's history you're reading, and just how far back you're willing to look.
Consider this staggering comparison. In 1808 CE, John Dalton published his famous atomic theory, arguing that matter consists of indivisible atoms. But over in India, a philosopher named Acharya Kanda conceptualized the exact same indivisible building blocks of matter way back around 600 BCE. He named these extremely small, indivisible particles Paramanu. That is roughly 2.5 millennia before Dalton's new system of chemical philosophy.
And Kanda's description is absolutely fascinating. He wasn't just taking a wild guess that big things were made of smaller things. He specifically stated that these paramanu were indestructible, spherical, and constantly in motion. Even crazier, he explicitly recognized that these atoms could form pairs or triplets, and that unseen forces caused them to interact. He was essentially laying down the conceptual blueprint for modern molecular theory and chemical bonding, thousands of years before anyone had a microscope to actually prove it.
To see how this atomic understanding was actually applied in practice, we can look at Ayurvedic medicine. In texts like the Charaka Samhita, Ayurvedic practitioners documented how to treat diseases by extremely reducing metals into what they called bhasmas. Fast forward to today, and modern analysis proves that these metallic bhasmas actually contain metallic nanoparticles. Let that sink in. When ancient Indian doctors were mixing up these remedies, they were effectively pioneering early nanotechnology.
Finally, Section 6, Ancient Matter, Modern Measurements. Let's see how this ancient grasp of matter perfectly aligns with the way we standardize science today.
Okay, keep our modern definition of a pure substance in mind. It has a fixed composition where all the constituent particles are chemically identical, and they can't be separated by simple physical methods. Well, that is exactly what ancient Indian metallurgists achieved. By rigidly controlling kiln temperatures, they successfully isolated pure gold and copper. Actually, their ancient kiln firing methods directly mirror the strict temperature controls we use in contemporary industrial smelting. The famous golden gloss of northern India's black polished ware, which honestly still baffles some chemists, proves they had absolute mastery over extracting pure substances from heterogeneous mixtures using heat. Our entire modern framework for classifying matter maps seamlessly onto the chemical processes used by ancient Indian scholars. We classify matter into pure substances, like the elemental copper they smelted or the compound sulfuric acid they synthesized. We have homogeneous mixtures, uniformly distributed, exactly like their complex botanical perfumes. And of course, heterogeneous mixtures with non-uniform compositions, perfectly matching the early gunpowder and fireworks mixtures of sulfur, charcoal, and saltpeter detailed in Tamil texts and the Rasopanishada.
Now, to systematically measure the properties of all these pure substances today, the global scientific community relies on the SI system, the International System of Units, established in 1960. Whether we're measuring mass in kilograms, thermodynamic temperature in Kelvin, or the amount of substance in moles, we rely on these rigid, globally accepted standards to make sure our chemical formulas and reactions are exact.
So the crucial takeaway here is this undeniable bridge between the ancient past and our modern laboratories. The rigorous empirical experimentation of ancient India, whether it was standardizing soap ingredients, maintaining exact kiln temperatures for pottery, or calculating precise ratios of plant resins for durable dyes, all of it directly foreshadowed the precise stoichiometric calculations and dimensional analysis we demand in chemistry today. They were observing the law of conservation of mass and the law of definite proportions in practice centuries before those concepts were formally named in Europe.
As we wrap up today's explainer, I want to leave you with a final thought to chew on before our next class together. When we really dig into the archaeological record and these incredible classical texts, the timeline of scientific discovery becomes so much richer and far more global. So, how much of our modern science is actually just a rediscovery of ancient ingenuity? Thank you for joining me today, Focus Learners. Keep asking questions, keep analyzing the data, and I'll catch you in the next explainer.